So just to talk about the agenda a little bit, I want to give a brief background about what are the use cases for the high resolution timers. And then I'll also talk about what a typical data plane application would look like. I'm probably going to keep it short because I see a lot of familiar faces who are already well aware of the data plane. Then we'll talk about the current timer implementation in ODP, and we'll look at what are all the factors that affect the timer resolution. And then I'll talk about the proposal or some of the experiments that ARM has done with respect to how do we have a high resolution timer. And then we'll look at some results and we'll have a Q&A on that. Okay, so first about the use cases. So there are a lot of use cases. So I'll take a very simple use case of IP reassembly, which probably everyone would understand. So what we have in reassembly is we have a set of fragments that are coming in from the network. And as soon as we get a fragment, we would have to allocate a buffer and store that fragment in the buffer. And now once we have all the fragments arrived from the network, we have the packet reassembled and it's given to the application for processing. But it might happen that the fragments are lost on the network. So in that case, the system has to go and free up its buffer. So the other problem that it presents is how long are we going to wait for all the fragments to come in? So that's where the timer comes into picture. So as soon as a fragment comes in, you say that, hey, I will allocate a buffer as well as start a timer. And if all the fragments come in before the timer expires, you are good. Otherwise, the timer expires and you free up your resources. So that's where the timers come into picture. There are other use cases which I'm not going to go into, but the important point is that different use cases require different resolution. For example, reassembly would require probably in terms of millisecond, but max scheduling might require in terms of tens of microseconds or hundreds of microseconds. So ODP needs to support all these use cases. Okay, so what do we have in the, how does a data plane application looks like in a multi-core system? So what we have is a set of cores which are reserved for the data plane processing. These cores, they pull the packets from the queues. The packets come in from the network and they get queued on the input queues. And then we have a scheduler which runs various policies like round robin or strict priority and takes the packets from the queues and hands it over to the application to process the packet. So then there's a control plane core which typically runs routing protocols or signaling protocols and configures the data plane cores with various tables, for example, the forwarding table. So now all these data plane cores have to run timers. We have a number of cores and all of them are running packet processing algorithms, and those algorithms require timers. But what we have in the system typically is one clock source. So from this single clock source, we have to derive multiple timers that are required by this application. So that's where the timer module comes into picture. In the current implementation, the timer module is running on the control plane core. So the data plane cores say that, or the application running on the data plane cores say that, hey, I want a timer. I want a timer for 10 milliseconds or 100 microseconds. So it calls a timer start API, And the timer start API is going to put that data in a data structure saying that, hey, I need a timer for this much duration. So that data structure is accessed by the timer thread. So the timer thread, in turn, what it does is it asks the operating system, hey, can you wake me up every certain duration? Let's say the timer thread has to support a resolution of 10 microseconds. It says, it asks the operating system, hey, please wake me up every 10 microseconds. And once it wakes up, it goes through its list of the timers and sees if any one of them has to be expired. If it needs to be expired, it sends a message and puts that message on the queues, input queues. So again, the scheduler comes into picture. It picks up that timeout message from the queues and gives it to the application saying that, okay, your timer has expired now. So this is how a typical timer works in a data plane application. So now, where is the resolution coming into picture, or what affects the resolution of the timer, right? So we will look at some of the latencies that are involved here. So first one is the latency in starting the timer. So, the data plane application is going to call this API to start a timer, and that API has to take this timer and put it in a data structure. But so there is some latency involved over there, but that is not something that the application cannot handle. The application can handle that, so we are not really concerned about that latency. The second latency that comes into picture is the delivery of the timer tick expiry to the timer thread. So we have asked the OS that, hey, wake me up every every 10 microseconds, for example. So when the operating system decides that he has to wake up the timer module, there's a sequence of things or a lot of software that it needs to go through, and that adds to the latency. The other latency is involved with the timer module itself. It has got a list of timers that it has stored in its data structure. So it needs to go through that data structure and see which timers have expired. So that process adds to the latency. So third latency is in delivering the timeout event to the application. So it has to enqueue the timeout event to the queue. Then the scheduler comes into picture, and it has to schedule that timeout event to the application. So this process adds latency. So the goal here is to make sure that all these latencies are reduced. So just to put this in a perspective here, the ideal behavior that we would want is the application starts a timer with certain timeout duration. The timeout happens, and the application immediately receives the timeout event. This is the ideal behavior that we want. But what actually we have is the application starts a timer. There's a tick expired. That's the 10 microseconds that we talked about. It expires. Then after that, the timer module has to go and process all the timers that it has stored. So I'm sorry, I think I stepped one step ahead. So that timer the tick expiry has to be delivered to the timer module. So that I'm calling it here as T1 for our reference. So once the timer module receives the tick expiry, and after that it has to go through its data structure to see what all timers need to be expired at that moment. So that is the T2 latency that I'm talking here. And then once it sees that certain timers have to be expired, then it needs to be delivered to the application. So that's the T3 that we're talking about. So from the ideal behavior, we have got all these latencies, T1, T2, and T3. And for the timers to be high resolution, the sum of T1, T2, and T3 has to be much, much lower than the actual timeout value. If this latency is higher, then we are going to lose the resolution of the timer is going to be very low, or very low or high, however we look at it. So for this exercise, our goal has been to reduce the latency involved in T1. That is, for every tick expiry, how much time are we going to take to notify the timer module itself? So we are just focused on T1 today. We are not focused on T2 and T3. We will do that at a later point. So, I just want to take a look at how the T1 values look like today with the current implementation. So what we have is this. So what I have done here is I have done 2 experiments. In the first experiment, the control plane is running only the timer thread. And in the second experiment, we are running the timer thread plus something else, because that's the typical use case. On the control plane, you just don't run the timer thread. You have your routing protocols and things like that. So we wanted to see, running those applications, how does it affect the timer thread? So if you see here, the T1 value changes dramatically. If I just run the timer thread, we are taking like 151 nanoseconds on an average to deliver the tick expiry to the timer. But if we start running some other application, it goes up to 2,600 nanoseconds. It's not only that, it's the variance in that latency. We want determinism. We want to say that, hey, this T1 needs to be within 20 to 60 nanoseconds, for example. But if we say that, hey, it's going to vary between 20 to 12,800 nanoseconds, that's a problem. So we want determinism, and we want T1 to be as less as possible. So the proposed changes look like this. So we have the DataPlane course, and they are doing the packet processing. And then we have a single clock source, and now we want timers. The DataPlane still calls the timer start APIs, which writes to a common data structure. But what we have done is we have moved the timer module from the control plane to the data plane. The idea here is to give better control over T1 to the application and not be dependent on the OS to schedule the expiry events to the timer thread. The other thing that we have done is, instead of the timer waiting for an event from the OS, it is going to poll the ticks. It's going to poll the clock. So once it sees that, hey, I got a tick expiry, it goes through its list of timers and going to expire them and put the timeout messages back onto the queue. So the rest of the processing remains the same. Okay, so yeah, as I said, we have moved the timer processing to the DataPlane course. Then instead of waiting for the timer expiry event from the OS, we are going to poll the timer. We are going to poll for the timer tick expiry. And then the other advantage that we get is now we have multiple DataPlane cores looking at the timer pool, or the set of timers that you have, instead of just a single core looking at it. So what it does is it also provides control over T1 for the application. Application can decide how frequently it wants to poll for the tick expiry depending on its requirement. So with this, we did some benchmarking. So this is what we see. So we have the data plane thread with one data plane thread and 1 to 7. And then we have done, again, two sets of experiment. In one experiment, we have the data plane threads, and we have data plane threads, and then running some control plane application to show that it does not have any effect on the data plane cores. So what we see here is, on an average, we see a latency of 100 nanoseconds. But even when we run with other control plane processes, it does not change a lot. It's probably because of memory IOs and all that we see a little bit of difference. The other key thing is, when we increase the number of data plane cores, the latency is coming down, because now there are multiple cores that are looking at the timer, the timers that needs to be expired. The other important thing is that if we look at this graph, earlier we had the T1, which varied from 20 to 1,200 nanosecond, 12,000 nanoseconds. But now we have it over a period of 20 to 200 nanoseconds. So the variance is a lot less with this approach. So yeah, with this change, we feel that application has got better control over the T1 latency. And our future work obviously would look at how to reduce T2 and T3. Yeah, so. Yeah.
So a couple questions. One is, if you can measure or estimate T1, T2, and T3,
yeah.
can you just adjust the requested duration to account for those?
Yes, that's one of the discussions we have had. So if I could measure all this, maybe I can try and expire the timers early so that the application gets it at the.
The second thing, so in this approach, you've got the timer running as a subroutine of the scheduler, similar to how packet IOs are handled. You have scheduled mode IO.
Yes, yes. So yeah, right now that has been done to provide backward compatibility. But I feel that it needs to be pulled out so that it gives better control for the application as to how frequently it wants to look at the timer tick. That's what is my feeling, but it's up for further discussion.
So I understand the pros, but doesn't it have a side effect on the data plane performance? So you have to actually constantly monitor the timer inside the data plane, which is, I would say, doing other job as well.
Yes, it is going to affect the data plane performance, but what are the alternatives? So the alternative that we have looked at is the control plane, and control plane also has got to do other work. So
one alternative is to use hardware, off, timer off, and you don't see any kind of issues on any core, because hardware
yeah.
will know all of that. So
Petri, let me.
Talking about modified Linux implementation.
Yes. Can I? Yes, I mean, if there is a hardware block that implements timer, it doesn't make sense to do this. This is for a platform where we don't have hardware, the timers implemented in the hardware, right?
One API, many implementations, and use the hardware support whenever you have it. So here is basically modified Linux don't have the hardware support.
Yes.
You can take one thread, one core aside, and run kind of in path and run the interrupts through that one, not through the core 0, which is kind of the Linux is running, making kind of all the latency kind of screws up your interrupt latency anyway on that core. So you should be interrupts and timer processing in one core and right there. So that's always
Yes, I mean, see, that solution works under certain cases and it doesn't work under certain cases. So if you have a system with few cores, right, it doesn't probably make sense to reserve one core just for timer thread processing, right?
Yeah, and it doesn't make sense if you don't use timers or if you don't require high resolution. So there's many kind of, not one solution fits all.
Yes, exactly. It's not one solution.
Yeah, but I mean that it's kind of bad to make the assumption that you can do this timeout calling from the schedule core always, because it affects the data throughput.
Yes, that's exactly what my point was. My point is, I don't think it should be part of the schedule call. It should be outside of it so that there's better control for the application to do what it wants to do.
T3 requires it to be part of the scheduler. Okay, because
Uh,
the timer cannot, a timer event cannot appear to a thread until the scheduler is called anyway. So there's no getting away from that.
Yes, but I believe we are talking about the timer thread that processes all these timers, right?
Forget about CLI.
Or the timer functionality, yes, timer functionality that process all this.
Event, the only way I get a timeout event is by calling the scheduler. How the scheduler
No, you need to call the scheduler to receive the timeout event that are queued on the queues. But the functionality of going through your list of timers and putting that timeout event into the queue need not be part of the scheduler.
But it's no different than the scheduled packet I/O, because that's exactly what happens too. I mean,
Yes.
there's a poll of the scheduler runs a poll mode on the I/O in order to get the queued, the scheduled I/O.
Yes.
You got the same effect for timers.
Yes, it is the same effect, but
It's a simple test to say, does this thread have an active timer? Yes, no.
yeah.
If the answer is no, you obviously there's nothing to do.
Yes, but if there is activity, now you've got to go poll the timer tick, right? So as I said, both of them are possible. If you want flexibility for the application, I believe it can be pulled out, is what I feel.
One important thing to remember is that the destination queue may be also non-scheduled queue.
I'm sorry, I didn't get that.
There are queues that are not scheduled, so it's also kind of application can ask that send the timeout into this one queue here, and application is the one that goes and dequeues from that queue when it wants to. So the target queue may be scheduled queue behind the scheduler.
Yes. Yes. So from the timer perspective, that does not matter. So from the timer perspective, what matters is give me a queue where I can put the timeout event. Yeah, I mean, what I hear is there's a need of more flexibility. Is that right?
I'm saying that there are many ways to solve this one.
Yes, definitely. Yeah. Yes. And I feel that providing flexibility is the way to go for that. Yeah. Yeah, there are those use cases wherein you want to say, give me a timeout every 100 microseconds, for example. There are cases where you want to cancel because it was not required. Okay. Yes, I think what you are requesting for comes in the portion of the delivery where the timeout event is delivered, right? So if you say that, hey, I want this timeout to be processed on core X, yeah, core X, and then you can have a queue that is polled only by that or scheduled only for that core. Yes. So if I look at where we want to do this per core packet timer processing, I feel it more useful when you want to create the timer. When you want to create a timer from a core, you would rather put it on the timer pool that belongs to that core, so that your data access is restricted to that core. But once the timeout event happens, it does not matter where that gets processed from a timer perspective. So if I had to give you some more details, so the timers today are in a shared data structure that's accessed by all the cores, which means that there's a lot of
What he's proposing is that the cores which did not register for a timer should not pay the price of the polling and all of that. They know they will not deliver a wake up to themselves, so they should just skip that step. Is that what you're saying?
Yeah. So I think we kind of, both of us are agreeing on a generic solution, but solution is a little bit more involved is what I'm trying to say. Yes, I am agreeing with the idea. Yes. Right now, no. We don't have like a packet processing workload. No, we don't have that. But it has some workload about collecting statistics and timestamps and things like that. So. Yes. Yes. Yes, at certain frequency. Yes. Yes. So one thing that we have to note here is that it's a single thread, right? The data plane thread is, actively, it's not getting scheduled out by the OS. It has control over the complete core. That's one thing. And what we are saying here is the frequency at which the timer module runs is in the control of the application. So the application can decide if it thinks that, hey, if I process 10 packets, I'm going to introduce more latency in the timer, then he can reduce that. So. Yes, yeah. And I feel there's more flexibility required in how the application can alternate between the packet processing and the timer processing. Petri? Yeah. Yes, yes. Yes, so this is where I'm trying to say that now the timer processing is in the application's control. So application, yeah, application need not process 100 packets, for example. It can say that, hey, I'm going to look at the timer every 10 packets. So. Yes, yeah. So if the SoC has a hardware timer, this does not have any effect on that. The same APIs are going to work for the hardware timers as well. Yes, yeah, yeah. Then, yeah. Yes. So it is about providing that control to the application. In the current implementation, we don't have a better control over that for the application. So. Yes, and implement optimizations wherein if a particular does not have any timer, then it does not spend a lot of time in that. I feel that's a solution that we are looking at. So. Yes, we are done, unless there are any more questions from the audience. Thank you.